Hello, and welcome back. We are absolutely going to jump right in for today's session with our full-length 2 review of Chem and Physics. And what I want to make sure we're clear on is that today's session should absolutely be saved until you have taken the full length. Now, I did notice actually that half of the students in today's session did take the full length and their score went up noticeably, so kudos if you are someone whose score increased, and about half so that their score stayed nearly the same as it had been on full-length 1, which hopefully you took in the past several weeks. That's actually relatively common. We tend to find that between the diagnostic and full-length 1, there might be a marginal score change, and between full-length 1 and full-length 2, usually we do see about a neutral or a slight positive increase in the majority of cases, but that doesn't necessarily mean that just because your score stayed neutral, you haven't been actively learning. Remember, putting into play a lot of the extra capital strategies, really trying to make sure you're utilizing the methodologies and you're doing good outlines is key to making sure that you continue to see the improvement you're really looking for. So as we go through today's session, I'm going to be tackling right off the bat our full-length 2 review of Chem and Phys, but a lot of what I'm going to try and throw in here are hints onto how we can more effectively use things like graphical equations, or hints on how to circumvent some of the extra math to make sure we get those points that we deserve on the questions that we do throughout any of the full lengths that we take from this point forward. And again, this is the sort of thing that you should actively be doing as you go through and do your own review of all of the full lengths that you take. Without further ado, again, we are going to be tackling some elimination strategies, definitely going to go through the intimidating math and make sure that you know the most effective way to tackle them, and then finish out with some viewing of different graphical information techniques and how to make sure we absolutely get all of the points. As we go through, remember, we are going to be tackling questions directly from full length 2, which hopefully you've taken in the past couple weeks, so it's still relatively familiar. But if you haven't taken it in a while, maybe from earlier in the course, I'm going to go through and just make sure we're all clear on the steps in the question sets. Also, as we go through and tackle things like wrong answer elimination, there are a lot of classic cases that you can hopefully help me out with as we tackle some questions. For example, right off the bat, question number 40. This looks like a relatively detailed IUPAC nomenclature question. I've got to do something from figure 3, so we're going to have to go through and tackle the different lengths of the chains and about the different functional groups and take a look at figure 3. But before we even go back to figure 3, one thing that I always tell all of my students is look for shortcuts. Look for maybe some shortcut strategy that might even help us avoid doing a lot of work with figure 3 for that matter. Right off the bat, I noticed that we're dealing with IUPAC nomenclature, and a lot of things seem the same, like the R chiral center. But is there anything that stands out as being noticeably different among the answer choices? Maybe that's something we can pinpoint and lock into to try and differentiate between. Yeah, the one versus the al, is this a ketone or is this an aldehyde? Now, certainly there's only one aldehyde, which stands out as an outlier. And besides the functional groups, absolutely, we have ethyl, methyl, or diethyl. So something about the structure. Do we have branching? Do we have splitting? How long is the carbon chain? And finally, and maybe the first one I might have grabbed onto, is what Emmanuel and Hannah put in here. The fact that the carbon chain is noticeably different among the answer choices. We have a pent, we have a bute, and we have a prop. So if we could figure out what the initial longest carbon chain is in the first place, that might actually get us down to the one right answer, if it's the pent or the bute, and maybe force us to choose between 2 answer choices if it's C or D, if it's only 3 carbon long. But between C and D, as Tristan already put in here, as soon as we get it down to C and D, if we had to, we would immediately between the ketone and between the aldehyde, a fast functional group to differentiate between. So taking a look at the picture, we do have, from figure 3, that it was a 5 carbon long chain. I'll put that back up here again. C2 tells us that we had the 2 carbons there in the end, just to make sure we didn't miss one. And then running all the way down the line, 1, 2, 3, 4, 5 carbons long, has to be answer choice A, pentanone. Now, of course, there is that carbon chain coming off of it down here in the bottom right, but again, that would just be something that would impact the fact that it's called ethyl, and honestly, not something that we would have spent a long time looking at on a question like this, because we already solved the problem. That's sort of the key that I'm going to be going through and tackling with you in today's session. How many people down here in chat, give me a thumbs up if you spotted a shortcut like this on question 40, or a thumbs down, a 9 if you missed this and ended up doing the whole IUPAC. It doesn't matter either way, but I want to talk to those kind of shortcuts. Okay, nice. Bunch of thumbs ups. Now, my takeaway from this, even though everybody here who's responded did use that kind of a shortcut, is to always be looking for these. When you go back through your full-length review and you hit a question, even when you got right, like this one, go back and ask yourself, could I have answered that question faster if I had just noticed the carbon chains were different? Or if I had just noticed that it was aldehyde versus ketone? Could I have avoided going through and doing the entire IUPAC name in the first place, which maybe we did accidentally without noticing we had a shortcut? That's my takeaway. And we're going to see a bunch more problems in today's session, but keep that in the back of your mind. As you review, it's not just important that you get it right. Ideally, it's important that you get it right in as short amount of time as possible, because it's going to give you the extra buffer to tackle future questions or future passages where you might actually need that extra time. Here's another great example, 2 questions later. Okay, we want to talk about this aldol condensation proceeding. Man, this has a picture, has a reaction, has a big chunk of text. Looks like it could potentially be, like number 40 from a second ago, a lot more work. Now, we can always triage. In our assess step of the Kaplan method, we can decide to move on or not. But I always encourage, take 3 to 5 seconds on any problem before you decide to skip it or mark it, and decide if it's as tough as it originally seems like it is. Now, it gives us some clues in here. For example, what's one major clue that we could use to work through the answer choices in the question stem? Or even in the picture, along with the question stem for that matter. Aldol condensation, exactly right, Mary. That's a huge hint if we've seen aldol condensations before. Now, how about in the picture? If we missed that clue, aldol condensation, what about in the picture is going to help us figure out what the answer choice should look like? Sure, Hannah, that's going to be helpful. I'll come back to that in a second. Even before we get to that picture, there's a lovely hint. Because remember, we're trying to get the answer as fast as possible. I would love to not even have to do the reaction. That's my hint. I'd love to not even have to do any work solving out the aldol condensation, looking for the actual electrophile, the actual nucleophile, figuring out which one backside attacks the other. I don't want to do any of that. Yes, definitely, Hannah. That will be useful. And you got it, Emmanuel. The starting material, it tells us is an aldehyde. My goodness. If we're looking for an aldehyde, then could it be this butanoyl chloride? Does that sound like it has the aldehyde ending? Answer choice A? Boom, no way. How about any other answer choices we could get rid of? Because they absolutely are not aldehydes? Yes, absolutely. Let's get rid of answer choice D, because we do not want to have the own ending. That's a ketone. We want the Al ending. Now come back to what Hannah asked a second ago. Oh, something about number of carbons? Yeah, we have a final product here that clearly has 6 carbons. Okay. Could we have we clearly, excuse me, I got thrown off by thinking about the butanoyl chloride, which I'm going to describe in a second ago. We clearly have, 4 carbons in each one of those top two, the top chain and the bottom chain. So could we have propanal, which is 3 carbon molecules coming together to give us an 8 carbon in the end? No way. Answer choice C, walk away from the problem. I mean, notice, we do not want to do the aldol condensation. We don't want to have to think about electrophiles and nucleophiles, even though, Hannah, your first point was absolutely valid. If we had had different things coming together, if we had had some sort of heterogeneous mixture of aldehydes, yes. We would have paid a little more attention to which one was the nucleophile, which one was the electrophile, absolutely. But doing as little work as possible is exactly the sort of smart points, as Kristen points out, as opposed to hard points. Now, I definitely saw your question about butanoyl chloride. Again, butanoyl chloride is not that bad for us to draw out. it would be 1, 2, 3, 4 with Cl on the end. That would be butanoyl chloride. Again, 4 carbons long for but, and then oil chloride, it tells us it was a carboxylic acid where the alcohol group was replaced by a chlorine atom. So butanoyl chloride is just that carboxylic acid derivative where we swapped out those two groups. And again, the same thing, butanoyl bromide, butanoyl iodide, all would be the same sort of overall structure. And going quickly from the name to a structure or the structure to the name absolutely is key for MCAT success. So if some of the IUPAC nomenclature is not 100% locked in, even though it's not going to be hugely important for Chem Phys, definitely it is a key piece for us to do well in biochem. Right, Hannah. And the oil chloride or oil halide in general is a very classic structure that we're likely to see untested because it is so reactive. We have a great leaving group and we have a great site of attack. So likely to see this usually as a reactant in some sort of organic molecule. Again, not hugely pertinent to most of the Gen Chem we're going to see, but definitely as part of the biology and some of the orgo overlap in Gen Chem, and then specifically in biochem. Now, similarly for number 48, this is some biochem again. We really have to remember that even though this is Phys and Gen Chem, we are going to see a bunch of biochem, a lot of organic chemistry overlap. So in a question like this that seems like it's doing a lot more work, we have long answer choices. They're all about slightly different things, the R, the D, the pluses, and we have to try and quickly work down through the problem. We want some sort of, hopefully, a shortcut. We want to try and eliminate as much as possible here. Now, there are a couple ways we could do this, but it's saying not true, which means the 3 wrong answers could be possible, or even must be true for that matter. And only one of these can't be true. We could do this a couple ways. One is to think about what other groups we know. Do we know other structures that form D versus Ls? Maybe we could think of one of those, or we could pull one of those up mentally. Maybe we know about glyceraldehyde. Maybe we know about D and L glucose, or mannose, or galactose, and we could try and compare that to this structure. Or the second way we could do this, if we're not familiar with D and L designations, is try and do some elimination based off of what we know must be true from the figure. Which one of those two, pulling up a mental image of D versus L you already know, or eliminating based on the figure, do you want to do? We could do both. It sounds like Hannah maybe wants the second one. Tristan maybe wants the figure elimination. Okay, so let's do that one then. Let's do the figure elimination. I'll also show you the other way, just so you're clear, but let's do that way first. So if we're unfamiliar with D and L designations, see we've even got that built into the slide we planned for this, then we can eliminate true statements. Okay, so let's look at the chiral center that we have in the figure. And you help me out. Is this R or S? No. Probably a handful of people are pretty fast at doing this, so I'll give you a second because many of us are slow. I'll raise my hand. It takes me a little while to do the different configurations because I like to take my time, make sure I know where that fourth group is pointing so I don't make a mistake. Now we do have a larger majority pulling for S, but a pretty close split here. So let's be clear. The S versus the R configuration is based off of the highest 3 priority groups. Clearly there must be a hydrogen in here, and the hydrogen is pointing towards the back from our perspective, since we know that the amine group is pointing out towards us. So we're actually looking at the front of the molecule, and we can do that designation. Highest priority is the highest atomic number. So which of the 3 major groups on screen is the highest priority number? Just to quickly review this for everybody, since we did have a pretty even split between R versus S. It is a nitrogen group, absolutely, number 1. The big, massive chain that includes that benzene ring is going to be our number 2 because it has more bonds to higher number carbons on it. And then our number 3 group should be over here on the far left, 1 to 2, 2 to 3, 3 back to 1. That looks like it's turning to the left. That's sinistrol or S. So nicely done, Tristan, Mary, Emmanuel, nicely done. That's our quick connection to the chirality. Well, that helps us a little bit. If this is the dextro and it is S, then what else do we know by definition because of enantiomers. Remember, dextro is like D, levo is like our L. Yeah, it must be the exact flip. You got it. For sure, Tristan. Right, Emmanuel. If dextro is S, which we just saw on screen, then levo must be R, which immediately gets rid of answer choice A because it must be true. Now, the other tricky piece, and I saw a couple questions come through the QA on the right-hand side about this, is the trick with D versus L and lowercase d and positive, negative, and all that stuff is keeping track of which is which. Positive D and positive L, capital D and capital L really stand for the dextro versus the levo configurations, which is very similar to our R versus S configurations. The lowercase d and the lowercase l, though, those correspond to the pluses and the minuses. Now, remind me down here in chat, the plus and the minus that we usually talk about, are those, yeah, those aren't something we can see on screen. You predicted my question, Hannah. Those absolutely require us to have some sort of optical information, some experimental details. Now, that's true for the lowercase d's and l's, as well as for the pluses and the minuses. They're essentially synonymous for our purposes. So wait a sec. If lowercase d's and l's require experimental data, and pluses and minuses require experimental data, then do we have any information that would help us determine between C and D? Well, you're right, Mary, we don't. So then, bonus question, could C and D both be right? You got it, Emmanuel. No, we could not have them both be correct. So wait a sec. Then if C and D can't both be right, since we don't have enough information for it, and because really lowercase d and positive tend to be synonymous, then we have to cross them both out. It must be answer choice B. Done. That's that sort of critical thinking shortcut that can help you eliminate a bunch of the extra work on a problem like this. To be clear, if you were really solid on D versus L, you could have done it this way as well. You could have thought, well, let's compare it to something else that we know. You got it, Hannah. The capital L is for left-sidedness, which is what we see here for L-glyceraldehyde. Yeah, absolutely. So we could visualize the structure we have here on the left, flip it up so it's flattened out structure on our screen, and then say, oh, this is clearly pointing off to the left-hand side. This is our L enantiomer. So answer choice B would be eliminated because what we see on screen is L. But it told us that this is the dextro version. So B, the levo version, has to be the D amphetamine because it would be on the right-hand side. Right-handed. Again, though, the reason I bring this one up second is because so many people mentioned, hey, I don't have a really good picture of all of the glyceraldehydes or all of the different carbs that I could think of that are D's versus L's, and maybe even more importantly, it's hard to visualize this wedge structure as a flattened image. That's fine. Then we would do the other method that I showed a second ago, eliminating true answers. Now, also, to be clear, R and L and S and D are not always synonymous. You could have an R chiral center in a D enantiomer. You could have an S chiral center in a D enantiomer, for that matter. It is not always the case that S is L or that D is R, just to be clear, because a lot of people do get confused by that. But one is visualizing what the molecule looks like flattened out, and the other is actually determining the chiral center. So I saw one or two good questions about this come through the QA, so I want to make that clear. We do have to look at the actual pinpointed chiral center to get R versus S, and all we have to look at for D versus L is the flattened image like we would do for any sort of sugar. Now, one more that's sort of a biochem throwback. Let's take a look at number 57, because this is also a great chance for us to really lock down some shortcuts, really, to trying to track down the right answer. because in this case, we're also doing, like the last problem, a not true of the compound. So the right answer isn't true about this thing, but often it's much more attackable to talk about what must be true about this thing. So help me out down here in chat. When you hit this problem, was there any answer choice that you immediately got rid of because you knew it was true, certainly by definition, as soon as we saw this? What can we get rid of right off the bat? Yeah, exactly right, Emmanuel. Well, if we've got the compound here, it looks like the compound has two big carbonyl groups on either side with an oxygen in the middle. That sounds like the structure we would have for an anhydride, and there's two carbon chains on either side, and they're 2 carbons long, so that's F. So this looks like it's ethanoic anhydride. Specifically, absolutely, answer choice A must be true. It is the actual IUPAC name. Okay, we can also probably get rid of at least one more. Mary says get rid of D as well. Well, if this is an anhydride, which we just clarified, then D is always true for all anhydrides. It is formed via dehydration. The water molecule has to escape off. All right, well, now we're down between B and C. Remember, one of these must be true, so we'll get rid of it. And one of these isn't true, and we're going to circle it. So Tristan said that, you know what I grabbed right off the bat is highly reactive. Sure, an anhydride, considering the fact that the vast majority of our environments have some trace amounts of water, is going to react with the water in the environment. But additionally, it is absolutely going to be reactive in any sort of solution, in any sort of larger scale reaction where we might have water molecules being produced. Yes, answer choice C is true. An anhydride should be a highly reactive compound. Now, it's not necessarily a dangerous compound in some cases, but it is definitely reactive for a wide variety of reasons. But just throwing back to some organic chemistry for a second, we have 2 different potential sites for attack. We have a relatively weak structural bond to oxygen that could be hydrated. We could have a proton come in here. We could have water come in here. There are a lot of ways that we could break down this molecule to make it absolutely release a bunch of energy and be super reactive. So we must end up choosing answer choice B. But also, just to be clear, B is also wrong. Remember, just because we're looking for not true doesn't necessarily mean that it has to be extremely obvious, like this case where we have an anhydride and they're asking you about dumping it into aqueous solution. They could ask us something about structural stability. They could ask us something about its ability to do resonance. Any of those types of other considerations could have come up here in the wrong answer. Hopefully, it was a little bit more apparent that B is the wrong answer, because if it easily formed an aqueous solution, that means we can dump this in water and have it easily dissolve in and form a lovely, stable aqueous solution. But we made this by removing water. So as soon as we add back in water, it will want to hydrate this oxygen group and break this back into 2 acid pieces. In fact, most of our anhydrous carboxylic acid derivatives are only able to dissolve into water at about 2% or so, because after that, they just immediately start making lots of carboxylic acid, and we can't actually dissolve any more pure substance in. So again, it's very susceptible to hydrolysis. It will immediately get taken up. It should not want to form any sort of aqueous solution, and certainly not easily. Boom, answer choice B. I will mention that a lot of people tend to get trapped on problems like this one and the last one that we did by, unfortunately, either overthinking the problem or forgetting that the problem said not. Anybody down here had that happen to them when they went back and reviewed this test? They found that they had forgotten the not by the time you got to the answer choices? And that's one thing that I actually like to write down on my scratch sheet. So Hannah, if this happened to you, Emmanuel, absolutely. And what Emmanuel points out is exactly this sort of thing I tend to find personally when I do these problems is I get it down to 2, and then I'm stuck between those 2, and unfortunately forget I was looking for the not true, and say, oh, well, obviously answer choice C is right, and then before I go to circle it, because I've done this so many times in the past, I stop and double check. Was there a not? Was there an except? Was all of the following but? And then make sure I circle the right answer. So on my scratch sheet, often if it's going to be a not true or an except problem, I'll put a little asterisk or a little X mark on my scratch sheet to remind myself this is a not true problem. And that little bit of a helpful hint can sometimes be just enough to make sure you don't fall into this sort of trap. If that helps out, do that in your scratch sheet to make sure you don't fall into that trap. Now, next up, I want to make sure we talk about the shortcuts again for doing some of the more complicated math. But before we jump in and do something like this, which happens to be a slightly lower difficulty math problem, I want to ask you down here in chat, what sort of problems do you face when doing math? What sort of trap answers do you fall for? What are the hardest math problems for you on test day? That sort of thing. Air out your dirty laundry list of why math problems are terrible. Go fast and make mistakes? Absolutely, Mary. By not necessarily multiplying by 2 or forgetting to divide by 5 or something, for sure. Final step, Tristan, that hits tons of people. They were asking actually for how much current would it be going through the circuit over 2 seconds, and you solve for 1 second. They wanted that times 2 at the end. Exponent stuff? Sure, Hannah. Or rounding errors, Emmanuel? Okay. Now, these are all, as you're noticing down here in chat, very common concerns that pretty much we all face at some point during the math. If it's something like the math is just difficult for you, like exponents or multiplying quickly or dividing by a decimal, for example, I highly recommend practicing 3rd and 4th grade math worksheets. You can look up 4th grade math worksheets online pretty much anywhere and find some free downloads. Do maybe 5 minutes a day. 3rd grade and 4th grade math. It'll seem silly at first, but this is going to help you get that much faster at doing the math. Now, if it's something like units, or if it's doing that last step in the problem, then we can talk a little bit more about that as far as jotting down good scratch sheet notes. For example, question 2. I like this one, and help me out down here in chat if you remember what you answered for this one. Was it A, B, C, or D? I'll put up a poll. We're friendly. We're doing this like a tutoring session. That's what I was expecting, Hannah. A lot of people hit this one, and it's almost 50-50. The number of students who get it right versus get the trap answer. That is how extreme that trap answer is. Okay, almost fell for it, Emmanuel. Figured it out, Mary. Good. Because this is a problem where we're clearly doing some math that is not necessarily as advanced as running through exponents or doing extensive work with units and dimensional analysis. It's doing something with some proportional numbers, halves, quarters, stuff like that. So they gave us some fancy values for days. Let's round them a little bit. Maybe not even rounding them to 14 and a quarter. Maybe round it to 14. Maybe around the 28 point something to 28. Keep it nice, keep it simple. So 14 is 1 cycle, 28 is 2 cycles, so we've gone through 2 half-lives. Awesome. 2 half-lives is a half times a half is a quarter. Great. Answer choice A. This is where we go back and talk about what Tristan mentioned a second ago. Making sure that we do the final step. And this is good in general, especially if the math problem involves multiple steps, because there's a lot of opportunity for us to feel like we got to the end, we did the 7th math computation step, and think we're done. But we don't want the sample that remains. We want how much has gone away. So 3/4 must be the amount that went away. I often recommend, in any case, whenever you see a math problem where you get to the answer very quickly, and you notice that in the answer choices, there's a distinct opposite answer. For example, if you're doing a lot of dividing by 2's, and then one of the answer choice is clearly having multiplied by 2 several times, or one of the answer choices is a power of 10, or 3 powers of 10, or 6 powers of 10 off from your answer, that sounds like there was some sort of unit conversion or some dimensional analysis, I always stop anytime I see that sort of a hint and make sure I didn't forget to change millimeters to meters. Make sure I didn't forget to divide by 2 in the final step of that problem because we had a radius of 2. Or forget to square, or for that matter, the radius if I'm dealing with something dealing with gravity or electrostatics. So watching out for the other wrong answers in a problem like this actually gives us a hint. Hey, the answer choices are all quarters or halves or small fractional values. Gosh, there must be the potential to make a mistake and end up with the wrong fractional value. See what I'm getting at? We're trying to get into the head of AAMC. They're setting up these wrong answers because they're common miscalculations, so we can overtly be ready for those. We can say, hey, common miscalculations include the wrong fraction. Wait a sec, was the fraction I got the right one? And I love this because this comes up a lot in other areas like genetics. Anybody ever gotten to the end of like a pedigree question or an allele distribution question or Hardy-Weinberg question and picked the wrong one? Pick the p squared as opposed to the q squared, or pick the one that was the recessive allele when you actually had solved for the dominant allele. Sure, but you get the idea, Hannah. These are the sort of things we really want to look out for. And we're going to do some more problems like this one, which is a massively long problem. It has tons of answer choices that look super tempting, but we're going to do the same sort of thing. Try and avoid overworking and try and just get down to the right answer as quickly as possible. Now, first of all, we're dealing with some electrostatic force thingy, and it would be great if I knew the electrostatic force equation. However, bonus question, do I have to know the electrostatic force equation to get this one right? Yeah, just relationships. Exactly right, Mary. I mean, it'd be great if we remembered this, sure, but all of the answer choices have a squared term in the denominator. All of the answer choices have a number, a whole value that's multiplied by it, and then this other number, 8.9 something or other. So all of them have the exact same structure. If the answer choices had had some of these inverted, if they had had weird relationships or some that had squares and some didn't, yeah, it would have been a lot more helpful to know this formula. But this is one of those cases where we can actually get the right answer anyway. Now, additionally, you read my mind, Emmanuel. That was my follow-up question. Wait a sec. If we've got answer choices that are split 50-50, like repulsive versus attractive, let's get rid of half of those so we don't even have to consider them. I'm going to take this all back off the screen for a second. Let's just delve into elimination. Can we get rid of some of these without even setting up the equation in the first place? So Emmanuel seems to think we can. Anybody want to chime in? What could we do? How do we know we can get rid of attractive? Because you're right, Tristan. We can get rid of attractive. We should not see B or D being correct. Yeah, positive, positive. Calcium ion we should always know is a Ca++, and sodium ion we should always know is an Na+. That should always be the case for all of our calcium ions, all of our sodium ions. So, okay, we have a 2 positive and a 1 positive, and they're, well, not gonna like to be near each other. Likes repel, opposites attract. So get rid of B, get rid of D. Now between A and C, I don't want to do any extra work if I don't have to. So let's run down through what we know. This first number thing is the same for both of them. The 2, whatever that relates to, is the same for both of them. The 8.9 thing is the same for both of them. The squared term is the same for both of them. Gosh, the only difference is C has a -2 and D has a -5. This is where units, you got it, Emmanuel, saves the day. Man, those units are so helpful. Because immediately when I saw this problem, I was like, all right, well, I mean, plug in the 4 times 10 to the -2 oh, it's not meters. Oh. So convert that. Then plug in. Because my units and everything else are SI units. They are all in meters. And if I had misread this too quickly and I had thought that this was meters 10 to the -2, or if I had unfortunately just plugged in without even converting the units, I would absolutely be pulled into answer choice C. But no way. We want it in meters because we have to have like units. No worries, Mary. A lot of people end up choosing C by accident on this problem because of forgetting units. Anytime we have a new value, anytime we have a new standard gravitational constant or electrostatic constant or free energy constant, whatever it is, double check the units, make sure they're SI, and they always should be, just to be clear. Make sure you double check the units, and then look at the other units of the stuff you're using. For example, we might have had to reference back to a passage, and the passage might have had numbers in millimeters, or might have had values not in Newton meters, but in joules. We just want to double check that our math lines up unit-wise. Otherwise, we could end up with a problem like this. Yes, and to Dom's response, I just revalidate what Dom already said. Absolutely. When I saw A versus C, the first time I saw this problem, almost circled C. I was with you. But then I was like, well, wait a sec. These are off by a factor of 1,000. Gosh, that sort of difference in answer choices between 10 to the negative 2 and 10 to the negative 5, that sounds like a unit problem. That sounds like maybe forgetting to multiply by a unit or divide by a unit. Let's just go back and double check, because I had actually misread this as 10 to the negative 2 meters the first time I looked through it. I didn't even consider it. But that second chance, that making sure your units are right, is so important. And I would have done that anyway, gone back and double checked my units before finishing up the problem. But seeing an answer choice that is a power of 10 apart just sends off warning bells anyway, just reaffirming the fact that we absolutely have to look for it. Now, just to be clear, if we had known the formula from the first place, then we could have plugged in for the m value in the denominator, and that would have helped us get rid of B and C, which have the wrong radius value in the denominator, because we want the 10 to the negative 5, at which point we would have looked at repulsive versus attractive, and we would have circled A. So what you see here on screen is just the reverse order. If we had really known quite well the formula, and we had jumped in with trying to analyze a 10 to the negative 2 millimeter conversion first, then we would have eliminated B and C first, as opposed to eliminating B and D first. The whole point, even with solving it the way you see on screen, is that we went through and quickly eliminated half of the answers. Go through again, eliminate another half of the answers. We're not saying you have to get to the right answer immediately all in one piece. In fact, that is often inefficient. And when you go back and review, try to find places where maybe you did a lot of extra work or solved the problem completely when actually doing it piecemeal would have gotten you the right answer faster. For example, a problem like 17 is another great chance to do that same method. Eliminate step by step as you look through the answer choices. Now, if we're dealing with photosynthesis, this might not be a formula that you've already memorized, but it's something you actually could have come up with. We know that CO2 and H2O become sugar and excess oxygen. That is photosynthesis in general. So even if you had remembered only that and forgotten the coefficients on here, you could still have put this formula on your scratch sheet. CO2 plus H2O equals sugar, C6H12O6, and O2. And then you could have solved by plugging in, oh, all right, so I'm going to need 6 carbon O2s to make 6 in my CO2. I'm going to need 6 waters to make the 12 in my hydrogens, and I need some oxygen to fill up the remainder. We could have figured this out if you didn't already have this memorized, as 6 CO2, 6 H2O gives us our sugar plus 6 O2s. So not something that would have been terrible, but if you had this memorized already, that saved you at least 15, 20 seconds. But let's suppose that we actually had to jump in and do the math on this, because as Hannah points out, the math on these sort of stoichiometry-related yield problems tend to be a lot more work than some of the other straightforward math problems. Luckily for us, we just have to set it up. However, we have to make sure we set it up correctly. The units have to cancel out. Moles versus grams have to cancel out correctly, because some of these answer choices are going to be set up not times 6, but times 1/6, or not 11/18, but 18/11. So we really have to make sure we have the right thing being compared. So let's see what we start with. We have 11 grams of H2O. What would I like to do whenever possible if I'm given a gram value and I'm trying to deal with some sort of stoichiometry? This is true in all cases for stoichiometry problems or yield problems. Go to moles. Whenever possible, convert to moles. Okay, so converting it to moles, I have 11 grams, and I want to know the number of moles in water. You always have the periodic table available. It's that little periodic table button in the center of the screen. You can click it, it can pop up. But there are certain values you're going to use a lot, like the weight of oxygen or carbon or nitrogen. You're just going to use those so frequently, you should have these memorized by test day because it's just going to save you time. Help me out. Weight of oxygen? 16, nicely done, Hannah. And 2 more hydrogens added onto that means our water had better be 18. So converting from grams to moles is going to be 11 grams divided by 18 grams per mole. Nicely done, Freddie. All right, Hannah. So, okay, 11/18 had better be the first step in our conversion. Carbon's 12. Nitrogen, anyone? $14. You got it, Freddie. Absolutely. Now, again, I don't want to make a big deal about memorizing all of the values. For example, we don't usually see a whole lot of use for neon, right, if we're talking about the second row of the periodic table. But often we see a lot of the halides. So knowing that chlorine is 35.5, for example, definitely could save you a little bit of time. And so as you go through a lot of the practice problems, notice that you see a lot of sodium, calcium, potassium, chlorine, a lot of the reactive groups. So if you know sodium is 23, calcium is 40, chlorine is 35.5, that's just going to help you not have to pick up the periodic table and block your screen. It might only save you a second or 2 seconds, but again, I don't want to overtly say memorize the weights of the first row of transition metals, because probably if you're dealing with a transition metal problem with stoichiometry, you're going to have to look up a couple values anyway. So oxygen, yes, 16 plus 2 makes an 18 for our moles, so cross out any answer choice that does not deal with 11/18. Boom, A and B are gone. Now, additionally, we know there's only 1 glucose made, and we're trying to figure out how much glucose per original 6 waters. So we have to have a 1/6 in our answer. Don't even go any further. We're done. It must be answer choice C. I don't even care about that 180, and sure, the 180 is the same on all of the answer choices, but we go piece by piece, eliminate, done. In fact, I argue we didn't even really have to pay a lot of attention to the 1/6 stuff, because our amount of glucose made is definitely a fraction of the amount of water that went into it. So even without actually calculating the 1/6, I would be looking for any answer choice that mentioned a fractional value. So automatically be expecting it to be answer choice B or C just right off the bat. And that's that sort of careful critical thinking that, again, keeps us from maybe overtly making a step. Yes, we kind of do have to do that step, but keeps us from having to actually do the math on it or spell it out. Same thing with something like question 50. There's some math here behind the scenes, and we could do all of the math, but we could do some critical thinking to think about what impact would this have without necessarily going through any practice math or any hypothetical examples. So let me give you a second to scan back over this in case you don't remember question 50. Great, Tristan. Great. And I bet, let me guess, that you went for B. Just guessing. Cool. I figured, because that's the most, first of all, it's the most commonly chosen wrong answer. So I have some benefit on my side to that guess. But also because of the way that a lot of people read this problem, unfortunately. Let's run through it again, just to be clear. It's asking us if we have an experiment where the measurement device was wrong. Now, we're not talking about psychology, where we're going to be talking about a systematic error. If you'd had your Psych Soc 2 session, you know what I'm talking about. But we're talking about an issue here where we've got a measurement that's off for every value, but we're talking about our efficiency with whatever that weight is. Now, efficiency is a great formula if you already have it memorized. It's the load times the load distance divided by the effort times the effort distance. And Dom, if you would, go ahead and toss that in chat, because I bet a bunch of people don't have that flashcarded yet. It's load times load distance divided by effort times effort distance. And that's our overall efficiency. We didn't actually need that formula, but it helps make this problem faster if you knew it. The reason we didn't need the formula is what we're trying to figure out is if this is across a wide variety of weights, then that 3 kilogram difference is going to be a lot higher percent of the faulty mass value for a lighter weight versus a heavier weight. For example, let's suppose we're measuring something that is supposed to be 4 kilograms, and we're off by 3 kilograms. Then a 4 kilogram measured value was actually a 1 kilogram object. That's a 400% error. Versus if this was a 1,000 kilogram object. 1,000 kilogram object, and we were off by 3 kilograms, well, it's only 3 out of 1,000. That's a 0.3% error. Massive difference in our actual efficiency measurements because of the amount of error built into a small value. So looking through the answer choices, it must be answer choice A. The efficiency will be most skewed by a smaller weight. And that would be true of anything we had to do with a different weighted object. So a smaller object versus a heavier object, even if it wasn't an efficiency measurement. That's why I said the formula Don put down here is awesome, but not even necessary. Anytime we would have to do something with that weight in another case, like putting work on that or figuring out the potential energy of it, any of those, the amount of error in a small object is going to be that much greater than the amount of error built into a bigger object. Now, bonus question. What if it had said not 3 kilograms greater? What if it had said 3% greater? This is a bonus question. Give you a second to think about it because it's brand new. What if it had said 3% right? Yeah, exactly, Tristan. Then you'd be golden. Then it would be answer choice B because the efficiency, the work that we did with that number, would be the same error built in for every single one of those lighter or heavier weights. Yep. So if you had misread this as thinking that we had a percent error, like a 3% error or something, then B would have been right if you had misread it as that. But unfortunately, as stated, that could be as much as like a 400% error for a 1 kilogram object, or like a 0.3% error for a 1,000 kilogram object. So something that we would have to pay attention to. Now, at this point, I want to do one more thing. We've been talking about critical thinking from the very beginning. We've been talking about looking for shortcuts. So let's finish out with some of the graphical interpretation figures that you had to do throughout this full-length test. And just as a reminder, graphical interpretation comes up throughout a lot of the Phys and Chem sections, like in, for example, our circuit diagrams, where we have to remember the direction that the current is going from the battery. It has to go through the resistor. We might have a speaker that's also a resistor giving off energy. We might have a capacitor somewhere in there, which would have that particular diagrammatic element to it. And we have to be able to read these carefully. So this is not from a question here. This is just figures that we also have to look at. Something like a circuit diagram I brought up here because this is a sort of systematic schema reading that a lot of people get confused by and end up missing points on. We didn't have this particular circuit diagram on this full length, but if you think back to prior work we've done, circuitry does come up, and especially if you've gone to these circuits 1 and 2 sessions online, these channel sessions, those are phenomenal for working down through how to compute resistance, how to compute capacitance, what to look out for in circuit problems. So definitely take a look at those. But as far as our full-length review from today's session goes, we didn't have any. So let's jump in with some of the ones you did have. For example, this IR spec question. Now, if you haven't already covered this, I like to go through with my students the fact that there really are only 3 IR spec values that you need to know for test day. Anybody remember them down here in chat? Only really 3 that you need for test day. We need the alcohol, definitely Hannah. We need the amine, and we need the carbonyl. Boom, Hannah, Mary, Tristan. Yes, everybody's got them. So the carbonyl is a sharp peak around 1700. The hydroxyl or the alcohol group is a broad peak around 32 to 3500. And then the amine is right around 33 to 3400 sharp. Those 3 should be enough to get you the right answer on test day. So scanning through the figure, we have a sharp peak. The arrow's pointing to it. It's down there around 1800. Boom, answer choice A, finished. It can't be alcohol. It can't be our amino. We're done. Now, methyl could have been tempting for a few people. Just to be clear, a methyl peak or any carbon-hydrogen group tend to be out there at the high 2000s to low 3000s. So this other peak here actually is likely the methyl peak, because a carbon-hydrogen peak is somewhere in that 2800 to 3200 range. But I've got a bonus question for you. If you saw something at like 2800 sharp and it was a carbon-hydrogen, how helpful in analyzing an unknown organic compound is spotting a carbon-hydrogen bond? Say it again. How helpful is finding a carbon-hydrogen bond in order to figure out what the structure really should be? Almost not at all, exactly, Mary, because we are dealing with hydrocarbons if we're talking about organic or biochemistry. So definitely not something that I would make you memorize, and that's why really the Kaplan method is memorize those three, because those are deterministic functional groups. If we see those, we really know what the structure should look like. Memorizing like a carbon-carbon bond or carbon-hydrogen bond is just not going to be an efficient use of your memorization space or flashcarding time. Simple as that. Let's actually do another one, which also is sort of a graph problem, but requires us to interpret a figure that doesn't have a lot of information for us. So right off the bat, we're dealing with describing sound waves at some point. This is definitely physics. Exactly, Hannah. We haven't done a lot of physics in today's session, but I wanted to review this one because it's easy to make a mistake on this if we misunderstand what's being asked. It's really, as Hannah points out, a basic physics question. However, we also have to know a little bit about the aural structures. Okay, let's start with physics first, and then we'll get to ear, Hannah and Tristan, because I know you're all over this. So let's start with sound. Clearly, the y-axis is speed of the wave, so it's like speed of sound. And the y-axis is time, so we're going through different parts of the ear. But different parts of the ear, I know that there's the air part before it goes in. I know that there's some bone part, there's some solid parts. There's clearly some liquid portions, like the endolymph. These are all different substances. So it would help me if I remembered where sound goes slowest and where sound goes fastest, because that will hopefully determine what A, B, and C mean. Fastest through a solid? Absolutely, Hannah. Every time. In fact, it is directly proportional. We have slowest in gas, medium in liquid, fastest in solid. And this is something that hopefully you have memorized already, but if not, the thing that always helps me remember it is all those old cowboy movies where they put their ear to the ground to determine if the train is coming or if someone is chasing after them, right? Because if a train is coming, they put their ear to the rail, you can hear it through the rail faster than you will hear it coming through the air. If a train is coming, that is your best bet. That always stuck it with me. Helped me remember, boom, solid, because I'm putting my ear to the railroad, goes through that solid faster, I know the train's coming. So if you're a train robber, that's what you should do. Also, Kaplan is in no way responsible if you end up becoming a train robber. Now, in the answer choices then, that means B, which is our fastest, must be a solid. So scanning through the answer choices, all we're looking for here is a connection to what should be solid in all of the anatomy of the ear. Boom. Hannah's got it, and I'm sure that we all could have chimed in. Ossicles. That must be the bone portion. That must be the hardest portion. Absolutely the highest speed of sound. Now let's do a bonus question here. What would A be? That's the lowest speed of the wave value. What would A be? That would be air, absolutely. Answer choice A. Exactly. Hannah, Tristan, Emmanuel, nicely done. Now, final bonus question, I guess. C. What would, on the graph. Exactly, Hannah. What would C be on the graph? Conveniently, they are A, B, and C in the answer choices. So yes, Hannah, Tristan, Mary, it would absolutely be endolymph. And this, the passage actually described endolymph to us in case we didn't know that that was the fluid portion. We could probably figure out endo is inside, lymph is like lymphatics, and figured out that was the liquid portion as well, just in case. And again, let's do one more question. But this is also a great graph question. I think we can tackle this with our last minute or two. Now, I felt the same way, Hannah, when I first saw this problem, because of the squiggly, weird lines, and they're trying to talk about a single loop circulatory system, blah, blah, blah. But let's look at what they've given us. Because they're giving us potential energy on the y-axis, and we actually know in a normal human body how potential energy could kind of have changed. I agree. I agree, Hannah. I thought the same thing. But let's think about this. It starts at the heart and goes through systemic and pulmonary, changes back, blah, blah, blah. Okay, single loop through systemic and pulmonary. Well, I guess we don't really know necessarily whether we're going through pulmonary first or whether we're going through systemic first. So we'd have to look for either something that deals with lungs early or something that deals with dipping into the body early. Because no matter what, we're leaving the heart, right? That's got to be our start point. So that's actually kind of helpful. If our start point is the heart, then dipping down and coming back up sounds like going through the body. Okay, that sounds tempting, but what is A missing? If we're just talking about going down, like to the extremities, then coming back up to the heart. And it's missing the lungs. At some point here, at least some portions of the lungs are superior to the heart, so we don't have any little squiggles showing anything above the heart here. Okay, so get rid of A. How about, what's up with D? Let's take another one of the extreme answer choices that looks like it has very few squiggles to it. D looks like the potential energy of moving the blood around isn't moving. The blood is staying exactly in the heart, right, Hannah? We don't want that. Okay, now between C and B, we've got what look like relatively similar squiggles. In C, it looks like we go up a lot, maybe dip down below, and then go back up again at the end. So within one pathway through the heart, just to be clear, should we go up consistently, drop down, and then go back up again in that same pathway above the heart? We could go into the lungs. That sounds promising. But shouldn't we go into the extremities? Shouldn't we dip down at some point? And exactly right, Emmanuel. That should be a difference in the distance that actually corresponds to how far we go down in the extremities versus coming back up for the lungs. So it must be answer choice B. We go to the lungs first. We go back to the heart, pulmonary system, drop down into the peripheries, and then, again, back up again at the end to hit the heart. It has to be answer choice B. Now, again, kudos for today's session. We cruised down through a bunch of graphical analyses. Earlier, we talked about some critical thinking with shortcuts to math. At the very beginning, we really tried to lay down that concept of when you review, don't just look for questions you got right versus wrong. Always be looking for those sort of shortcuts. So great work in today's session. And as always, if there's anything else we can personally do to help out in today's session or explain questions, let us know. But we cruised through every single one right on time.